So, my name is Colin. I'm gonna talk a little bit about what Android SafetyNet remote attestation system is, and how it works, and why you should use it, and what you should know about it in general. Some background. I've been doing mobile stuff basically since forever, starting with Palmer stuff early in the day, and then doing Windows Mobile, SMS stuff a lot, and then a lot of Android stuff. I worked for multiple mobile device manufacturers. We're on mobile app security teams, and in generally I like finding bugs and reporting bugs in devices, mobile OSs, mobile apps. Been involved in a few things, and the most, I guess, more well-known things like the Android Hacker's Handbook, and I've recently worked on a developer guide for making smartphone apps more secure for the European Union Network Defense Agency. Those are the book is obviously not for free. The guidelines are for free. Okay, so what are the goals of this talk? The main goal is understand and what Android SafetyNet Attestation is, how to implement and deploy it, and when you do that, you also want to know, hey, what can this actually do for you, and what can it not do, and that also leads to what are known attacks and bypasses. But I'm going to present something new. And the big part of why I wanted to do this talk is because I thought the official documentation from Google about this is pretty bad. It's gotten better over the last 1.5 years. But the main idea when I was starting was hey, this is actually pretty cool. Nobody knows about it. Nobody probably really is able to really use it because the documentation is kind of wonky. So this is obviously about securing mobile apps, and mobile apps are only interesting if they actually communicate with something with your backend service, and you want to of course make your app secure, because then your users are happy, you are happy, you're making money, and everything works as expected, right? And you just don't want your app to be insecure, because then your customers and yourself are pretty unhappy. So mobile app security is really a thing these days, and your app is mostly a gateway to your backend service, and there's these days a lot of mobile first or mobile only applications, which basically there's only the mobile app is the only customer facing thing. So it's kind of important, and it's important because a lot of apps they really control the access to the content. Say something like Snapchat, it works only on your phone, and they don't want you to store pictures that you should only see for 5 seconds, stuff like that. So it's really about mobile app security. Is really about protecting your service, your revenue, your brand, and of course your users and customers. So what are the normal attacks that you see these days? It's OS modification, or they're better knowing as rooting or jailbreaking. And it's that's really about breaking the assumptions, because your app assumes, hey, if I store something in my private store, the user cannot just read it. Or you cannot take screenshots if I don't want to allow it, or my app is not going to be instrumented. And then there's, of course, app modifications, which is basically the same thing, but you don't modify your underlying OS, but just the app to do something else. And then there's the whole class of network attacks. Most of these, I guess, are solved these days with TLS and third pinning, if done right. So what is rooting? Basically, these days, all of your phones and tablets, you don't have full control over them. That means you don't have system-level privileges, and rooting is basically you try to get those privileges back, and that to access any resource on the system, do anything you want to do, without having the OS telling you, hey, you can't do this to this app. Reading and writing arbitrary files, and then of course modifying parts of the actual OS And on Android, this like really highly depends these days on the Android version because SE/Linux sandboxing got much better over the years. But yeah, this is like completely like different discussion. So if you look at app security in the old days, this was like, hey, I'm just gonna see if like somebody installed the SU binary on like my phone, and if that's true, like I'm gonna tell the user, hey, your phone is rooted. The same with like the UI applications to control access to Zoo, or if you have some instrumentation framework installed, it's like, hey, is this package installed? Or is like, hey, is like the device ID 0, that means like I'm running in an emulator. So that's basically what every app back in the day used to do. But it's like basically hard-coded checks. It's very easy for developers to like, hey, I understand if I look for this binary, then I can just like say, hey, you can't run. So it's like hard-coded checks are really easy to understand, implement, and deploy. But it's also for the attacker, it's very easy to understand, circumvent, and then still abuse your app. So normally, you just don't do that anymore. These days, what you do is you run checks by collecting data on your client and then just like do all the enforcement on your backend. Because then like an attacker cannot just like patch out some checks, but it has to like know actually what kind of data is looked at, and you have to like do much more work. And so there's been like companies, I guess, to like provide the service, but I guess Android or like Google thought, hey, we should have this as a platform service, and that's what like SafetyNet Attestation does. So SafetyNet and like all of Android security relies on something called like Secure Boot, which you also have, or on like other platforms. It's basically you just make sure you're like only executing trusted code by like verifying signatures like of the kernel and your file system during boot up. And then you have like stuff like SE/Linux restrictions for like building sandboxes. And then in addition, Google started building SafetyNet. And SafetyNet is really just like a brand name for like their platform security services, and they have a bunch of them. They have like verified apps, then check if they have potential harmful applications, which is basically, hey, is this like malicious app? Then you have this attestation service, which this talk is going to be about, and you have like now a capture service also. And all of this is really designed to run on like any Android device. It's just like part of like Google Play application of the Play Store. And it's really designed to be run on any device, no matter if like Google, Samsung, LG, whoever made it. And yeah, the attestation part is really about device and app attestation. And Google uses the SafetyNet Attestation for their like own apps, like really heavily, for example, for Android Pay, to basically make sure devices where they like allow Android Pay to run like are not rooted and apps are like not modified. And one part of that is because still like Google doesn't have control over like when some other company patches their device. So it's like, hey, if we just have our own service, we can at least do some basic attestation of the device like our code runs on, and then we can say like, hey, you cannot run like on a rooted device. So for them, it makes a lot of sense to have like a little bit of a trust system in the entire platform, not only in like their own Nexus devices. So what is attestation? It's really about determining if like your device or app was modified, and the idea is really to like not have developers build and develop like their own checks anymore. And as I said before, it's part of the Google Play services. It's like updated independently, so you don't have to like update your Play services application, but like every time you trigger like a SafetyNet attestation check, they actually download code. And like that code is like signed, and like there is a decent blog post about like how that specific part works, but they update that like all the time. And it's basically just like an API call to like determine if your device and app are like benign. Yeah, this is, yeah. So when I started looking at this, I was like, hey, yeah, this is cool. It's just like this like API call and like everything works. And the documentation was like pretty horrible. And it's got better over time. You like every time you would check and it's like, oh, maybe they did something. And then you would suddenly find new features in like their attestation system. It's like they're like not documented, which I'm going to talk about a little bit later. But yeah, like I don't really remember actually how well it was documented 1.5 years ago, but I remember it being like very, very shitty, or not good enough to like have it like an easy time. So how does this actually work? They have like some sample code, and their sample code uses like some fancy callback mechanism, but I like to have I just like made a short example using like just like an asynchronous way to call it. So basically, you connect to the Google API client and say, I want to talk to the SafetyNet API, and then if you get a connection, you just say attest, and then you depending on your network connectivity in your device, you will get a result. And in this example, I don't use an API key. The API key you really only need like for if you like want to prevent getting rate limited. Yeah, it's just like another parameter to the API. That part is actually well documented. Okay, how does attestation actually work? So in the middle, we have like our phone. It's like the guy in the middle, and it runs like our app, and also it runs like the SafetyNet Attestation service, which is like just a part of like the Google Play services APK on your phone. And then we have Google Play, which is just like the Google backend services. And of course, our app has a backend, because if your app doesn't really have a backend, all of this is completely useless for you. So say you want to like log in or do some interesting operation on your backend. Your backend will start and say, hey, can you please run this attestation for me? And it's basically like request the app to do something. The app then will just like call the SafetyNet Attestation API on the phone and will say, hey, can you please start this attestation? And then actually the safety attestation code on your phone will start and like inspecting your phone and inspect like the app that was calling the API. In this request from your server, you should like include something like a nonce, which is like a number used once. It's basically just like a unique token to prevent that like the result of that attestation can be replayed against yourself. Yeah, you want to have something like that. And basically this inspection step, that's what you like use to implement yourself. And it's like, hey, is this like SU binary on the disk? Is like maybe the system partition mounted read-write? Something like all of those checks are now run by like the SafetyNet Attestation client. And Google can really update this client like with any time they want without you doing like any update of your device. As long as like the Play services has the base code for running SafetyNet, they can like update that all the time, and that gives them very like fast reaction to happenings, which I'm also going to talk about later. So then the SafetyNet Attestation client is finished collecting all the data, and it just sends back the data to the Google backend, and they just like do some number crunching, and they determine like the status of your device, and then they forward that the data back to the Play Services API client on the phone, and that forwards it to your app, and your app should of course forward it to your own backend. And to make sure nobody can tamper with it, this is like cryptographically signed by Google. And then on your backend, you inspect the result, and then you can determine, hey, will I allow my client to do XYZ on my service? This is basically what you get back, just like a blob of a JSON web signature object, which is just like a certificate chain, like some attestation data and a signature. It's just base 64 encoded data. And yeah, you really need to like validate the signature. They have like some documentation about it. Google has an API where you can basically upload that blob, and they will tell you if the signature is valid. But they say like you really should not use that. It's just like for development purposes. I never used that API. I just directly implemented the signature validation myself. So in the actual attestation data, this is like how it looks like. You get back a JSON object, which has a number of fields. The CTS profile match, that's the basic check. That was like the original idea. So the CTS is like the compatibility test suite of Google. So like every time you make an OS image, like a new Android firmware versions for like your, say, if I'm a device manufacturer and I build a device, I have to, in order to get Google apps, I have to like run the CTS test and submit the result to Google. And the result of the CTS test is, one part is just to like verify that, hey, that company is like making a good, or like conforms to like our like standards. But it's also, they also use that data in the SafetyNet attestation. So they like collect some information from your file system and then compare to like the data the manufacturer submitted before. And if that data looks good, then the CTS profile match, the first bold entry, that will be true. And then you have the package name. That's basically just like the which package on the device called the API. And then you have a SHA-256 digest of your APK. And then you have like your nonce. The nonces, I think they say like you have to have at least like 16 bytes, but you can actually put multiple kilobytes in there. Yeah, I played around with it a little bit, and yeah, I think I got like up to like 4K or something. But like 2 kilobytes was like, at least worked. And then you also get like an APK certificate digest. So basically like the digest of your, of the certificate that was used to like sign your application. And then you get a timestamp. And then there's also the basic integrity field. That was something they added about a year ago. And it's a little bit weaker check. It basically just says, hey, like it seems like your OS image is not really modified, but we found like some binaries that indicate like you have installed something like SU or something on your system. So it's a little bit of weaker check. So it's like for, so then you can like determine, hey, am I good with routing as long as you didn't like super like modify your OS? Yeah. This is like the official like validation table from Google, where they say, okay, if this field, if the CTS field is true, that means like your device passed the test. And you have all the different values. Like on your device, you can see, hey, if you just unlock your bootloader, you'll still fail CTS, but your system will be still like set as like it like passes basic integrity. And they have a bunch of these different values, and a lot of these like indications also like highly depend on your Android version, which is absolutely not documented whatsoever. And I'm going to talk about this a little bit later. But basically, what you want is, if you're like serious about using this, then you're only interested in basically the state where like CTS is true, and you don't really care about the other states that much. You can, if you say like, yeah, I'm fine with routing as long as like not super heavy modified, but because Google will only tell you, like, give you a true or false value for either of these indicators, but they will actually not tell you like, hey, this is an emulator or this is that. They will just say true, false. So you're like completely blind anyway, and that's like something that's like very annoying. So I've built. Obviously, I integrated SafetyNet into like a real-world application, but I'm not going to talk about that. So I made this like small demo application, which I'm going to use throughout like this talk. This is just like the default, if everything is okay. Basically, the app just like runs a check against itself and then calls back to my web server to check also the application integrity part, because that part you have to like implement yourself. You only get like a digest. Anyway, this is like the ideal state. This is like an Android 6 device. It's like, hey, secure boot is there, so your bootloader is not unlocked, and you didn't change like the OS, and SafetyNet is actually available, and it also passes like all the tests. And below you see again, I just like print out the this blob. So of course, error cases. This is of course, like SafetyNet is of course like a network-based service. So you run a local check, and then you send like this the data back to Google, and then Google sends back data back to you. So a lot of things can go wrong. So they have a bunch of error cases, and one of them is just like, hey, like something went wrong, and then you get no. And then you just like get like an empty field, and this is like not really. They have this like as a tiny footnote, like, hey, there might something happen, and you just get like this error field set. Turns out like they just like give you like a blob that looks like this, and that means like hey, your API works, but something just runs wrong. And normally, how do you get out of this? You just retry and retry. So you have to be like very, very vigilant about implementing retries and error handling. Otherwise, this like API is kind of like useless. There's another like nice and halfway undocumented state, and that is when they say, hey, like the documentation says we can't determine which APK called us. That's why we're returning this. And it's like, that's like one of the core functionalities. Like if you like send like an RPC on Android and you don't know which other packet called you, that's like I don't know. So the documentation says we can't determine the calling APK. I'm pretty sure it's more like, hey, we can't trust this device at all, so we're not giving you even like anything about your app because it's like this is like super sketchy, and that's also like, yeah, unfortunately like a tiny side note in their documentation. So when you like implement this and you look at this, and it's like, yeah, why are like fields missing? Because one of the things you of course do is like you get like this JSON blob back from the API, and then you first validate like, hey, is this actually, does this have all of the fields? And then it's like, why doesn't it have like all of the fields? And then you like look at it and it's like, huh, this is kind of strange. So that's another not so nice thing. Especially like in cases where you maybe just like think, hey, I don't really care so much if somebody like modified the phone or rooted it. I just want to know if like my application was not tampered with. This like doesn't like help you like at all. So basically that's how it works. So your app is just calling, your backend just tells your app, hey, run this attestation, and then your app like runs the attestation, and then Google does something, and then your app like sends back the attestation to your backend, and then you say like, yeah, access denied or access granted. I wish it was like really that easy. There's like, unfortunately, like much more, especially like error cases. So all of the API calls, all of the different calls will fail in the wild all the time. And so one solution is you like have to retry, but at some point you just like have to error out, and just really the best solution is to like just report all of the different API error codes back to your backend, so you can make an informed decision about what to do. So and you have like these two stages. Excuse me. First, you have to establish like a connection to the Google API client, and that can obviously fail. And then you can have like this in the error cases where like your Google Play services doesn't actually support SafetyNet yet, and the only solution to that is you have to like update SafetyNet. That's why I had this button in my app where it's like, hey, force like an update for Google Play services. And of course, the attestation API yourself, like it will like error out if your nonce is too short, which like should really not happen after like you read the documentation. You can get rate limited, and that means like, hey, maybe you like should put the API key in your app. And then there's generic errors, which is just like, hey, this failed, or like you just got like a zero, like a null string back for like the attestation data, and that happens all the time. Like this is like just like the normal mode of operation. All of this has to be handled for in your client, in your backend. If you don't do that, people are gonna like just bypass it. Yeah, and that's like, so if you run it on, like say an old device, and if your Play service is like too old, basically we'll just get this error 2 back, and this means like, okay, like I can't do anything. So if you're like running or trying to protect a commercial app, you really have to like think about like, what do you want to do? Do you want to like force all of your users to update that? What do you do on devices where you cannot update that? Which those devices should not exist anymore. Like if you have a 4.4 device, you can update that. I don't actually know if you can update it on 4.0, but like all of the current devices that are used should be able to like update. And it's fun. You can just like go into like the settings on your phone and just basically say like remove all updates for like a specific app, like even a pre-installed app, and then you can like on 4.4 devices you can go back to this state and then to play around, and you will see it's like, yep, nothing works, and that's definitely like a state you want to like or be able to report back to your backend. So it's like, hey, that device is not updated. Yeah. So what do you do with like all of these API failures? Basically, what also the documentation says, you should retry, especially for all of the generic errors and network errors. Of course, if your phone is not connected, like doesn't have network connectivity, this won't work. But if your phone is, if your app needs to talk to your backend service, that doesn't really matter because you won't be able to like use your app anyway. But that also means you have to make sure if your app has like an offline mode, you don't like block on like, hey, I can't run attestation, I can't run attestation. Yeah. And then of course you have to like inspect this JSON blob because you don't want to like just like if you see like this error message in the JSON, you don't want to like send that to your backend service and then like restart the attestation. That's something you can just like do locally. And there's yeah. But if that fails, you of course also like have to finally at some point report that. But for like a few retries, that's like you should do that on your phone. And again, like if you don't report like all of the different API failures and back to your backend service and have like a really good plan on what to do, like either show the user some dialogue or maybe or have. It really depends on your app, but you have to have a plan because otherwise it will just patch your app and return like, hey, like your Play services does not have SafetyNet enabled yet, and we're just like, oh yeah, fine, the user can just use it, or just report like a generic like network failure all the time. And if you say like, oh yeah, if the network fails, of course you can use our service. So you have to be like very careful in like reporting error messages. Also, if you use all the error messages from the two different APIs, you can make a more informed decision because stuff needs to match up. So if you see like, hey, this one thing works and this other one fails in this strange behavior, like if you can get like a Google API connection, but say like you have a network connection on the SafetyNet attestation, that's probably like false. So you have to like know what kind of error states are like possible, and there's no like infinite amount of combinations. It's just like a bunch. Yeah. So now that you actually have like all of this like attestation data on your backend, and you can just for like the device integrity, you just have to like, hey, I just like look at this two fields, and if they're both true, your device is fine. But you also want to know, is your app like untampered, unmodified? So what about app integrity? And you have these two fields. One is the digest of your APK, and the other one is the digest of your certificate. So APK or app integrity in easy mode is you just compare the certificate digest to yours, and then you know, like, hey, if the certificate digest is the same, you know, like this app was like not repackaged or like modified because they hopefully don't have your private key, so they cannot re-sign it. Also, say you have 20 apps, you only need to like, if they're all signed with the same digest, you can kind of like hard code your digest, your certificate digest in your backend and just say like, hey, everything that's signed with this key is fine. So that's like really straightforward, easy APK integrity. The more advanced mode is if you actually check the digest of the APK itself. But of course, you're probably gonna like do updates maybe weekly, monthly, so you probably have a lot of APKs out there that you want to like allow on your system. So you have to be like really, really careful about collecting all of those digests, because if you miss one of those digests, he will say like, hey, we don't know like this APK, so we're gonna assume you modified it. Yeah, and that's not good. If you use this method, what you can do actually is something like you can have your developers like actually sign all your APKs for testing, and then just in the release process, make sure you like also collect the digests for the APK. And the nice thing is, like, say you found like some random, like a bug in one of your APKs and want to revoke that version. It's very easy. You could just like revoke the digest, or remove that digest from your database, and then it's like, yep, that version is now revoked. But yeah, you have to have really good control over your release process if you want to like use this method, because otherwise you will shoot yourself in the foot like really badly. But yeah, for most people, like the easy mode is totally sufficient. So it's a short like intermediate summary. Basically, on the client side, you have to check some error conditions and do retries, report all your failures to your backend, and your backend has to like validate the signatures, check the attestation states, check all the fields and like timestamps. So you can also, in addition to make sure like your nonce is correct, but you can also just like look at the timestamp, because the timestamp doesn't come from your device, it comes from Google. So you can say, hey, we accept like attestations that are like maybe 2 minutes old or something. You don't want to make that time window like too short, because yeah, like you should not like check like, I guess, below like 10 seconds or something, because like there's just like too much. But you should like check to say, hey, this is like not a year old or something. And really make decisions and planning for API failures, because this will like really happen all the time. You have to like decide if you're gonna like ask users to update their Play services, and you may want to like think about whitelisting certain, say certain customers or users or like kind of devices for like not being able to like update something. And you really need to be able to like have this kind of whitelisting mechanism, otherwise you will cause a lot of pain for like your users, and you don't want your customers to leave just because they got like a device that has like some weird behavior. And devices do have a lot of weird behavior when it comes to this. So now you basically know like how to implement this, hopefully in a decent way. But for me was more interesting, hey, so like we got this running and this seems fine, but can we actually trust it? How good is this? Are there like any limitations or Android versions? Can I like attack this, or can I bypass a check? And I guess every time you like, use a third-party like security system or mechanism, you really want to know if it is it actually like useful, because yeah, when you set up like some like firewall, you will also like try to like, hey, does this actually block this port after I configured it to like do that? And So basically, I took a really deep dive into like see what you can actually do. First, I looked a little bit like at like Android versions. And Android 4, like 4 and 5 didn't really have any kind of secure boot indication. Like they have secure boot is there, but you can like OEM unlock the device, refresh your bootloader, but that's like not visible to like the application on top. With Android 6 like and up that changed, you actually like know about this. So if you have attacks that rely on like an unlocked bootloader, they kind of all work on Android 4 and 5 devices. And that's like mostly about like routing. You have like a custom you have like maybe a custom bootloader, and you can do those attacks. And like in Android 6, then the boot state is like visible to like the user land, and SafetyNet like picks up on that and says like, hey, if you unlocked your bootloader, you're gonna fail. So I'm gonna do like a small demo around like Android 4, and you can very easily see that like SafetyNet is really mostly like looking at the file system of the device, and who knows what DM Verity is? Basic DM Verity is like a mechanism to have like a verified or like a cryptographically signed file system, or like not actually file system, but like block device on Linux. And Android 4 didn't have support for that yet. So you basically, as soon as you get root on an Android 4 device, you can just like remount the system partition and just like write files like SU binary to the file system. And you can very easily make SafetyNet believe that your device is actually totally fine while still having like a root shell on it. And that like it shows you easily that most of the all of the SafetyNet checks I know about are purely file system checks, so not like, hey, is there like a process running as root that like should not be there? So let's see. So this is an old Nexus 7 tablet with Android 4.4. So this is what did I do? So this device is currently it's gonna quickly. So this device is like currently rooted. So in system X bin, yeah, we have like Sue and daemon Sue. So we now run our little application. Let's see. So you see. SafetyNet is available, but there's no, the device is like non-compliant, and it's rooted. And you see on the low side, it's like there's like an advice down here. I have a screenshot of that later, which basically says like, hey, restore your factory image. So now we're gonna do. What you can now just do is just like we have a root shell, and so like we temporarily would just want to like bypass the attestation check. So we just like copy local data. And now what we just like, let's go back to this one. Oh, yeah, it's already like refreshed. And Now it's like, hey, we're totally compliant. And like a lot of like the SU managers these days, that's what they do. They basically temporarily hide certain files on the file system, and then your app is just like, hey, attestation is fine. Yeah, that was the first small demo. Yeah, so it's like really, it's very like heavily file system based, and you can yeah, easily do that, some bypasses. So yeah, on Android 6, if you have like Android 6 like has like the indication of like your secure boot state, and then down here you see they actually in their attestation now they just like added this new feature called like the advice field. They say like, hey, if they see like your device is like not rooted or like not modified, but you just unlocked your bootloader, so it's like, hey, just relock your bootloader and then you're gonna pass this test. Or if they see like on the Nexus where they said like, hey, you did some modification, maybe you should like reinstall like your firmware. And this is like purely informational, and yeah. So people have been starting to, when like SafetyNet came out, to like basically, like they had like all their routing tools, but now none of them would like allow them to like use something like Android Pay, because SafetyNet would say like, nope, not for you. So there was, people started like, I think from the Super Sue community, they started like SueHide, which is basically, they're trying to like hide certain things on the file system and move stuff around for like SafetyNet to not find them. Just like I just say, just like instead of having the SU binary in like system Xbin, just put it somewhere else, changed like the path name and so on. It was like, yeah, this is fine. There's some good documentation on this one blog post about SueHide. And then over time, like Google were like, basically they started like, hey, that's like kind of not cool, so they started building detections for that, and then they started to play like a cat and mouse game with that community. And I think the current like best one is like this Magisk, and that like also works like on newer Android devices, which is like, but they heavily like tamper with like the device. You have to unlock your bootloader, modify like your SLinux policies, and then like they inject a bunch of code here and there, and then you can like hide the routing from like specific apps. So because normally you want like stuff like maybe your shell or like maybe your like modding tool to like have root, so they can like inject code into other things. But then you want like apps like the Google like the Android Pay app to like not see all of this. So this tool is pretty good, and you see they actually like integrated like a SafetyNet check. So while they're developing, they can very easily just like, hey, let's see if they still see us. And yeah, Google is like really like chasing them down. You can like see on like the XDA developer forums like, oh man, like since like yesterday my Android Pay doesn't work anymore. And then like people like, yeah, they added a new check, and then like they bypassed that again. And you can like see like a constant like arms race going on, which is pretty good, because every time they break something, Google fixes it, and your app becomes more secure. It's like really awesome. But yeah, so most of like the prior research on SafetyNet has been done around rooting the device, or like having root and not being detected by SafetyNet. Nobody really like looked into the app integrity part, which I guess for most companies is a little bit more important, because they actually want like people not to modify their apps, because if I can modify your app and not modify the OS, I can just like dump out the data that I should not be able to like save without you detecting it. So yeah, so I was like, hey, let's look at like the app integrity part. And like the goal is really to like, I want to modify the app without triggering like the SafetyNet attestation, so without like tripping like either the APK or the certificate digest. And if I can do that, I can like do like arbitrary changes to the application. For example, hey, let's just like remove like your TLS cert pinning support, and then I can also play with your traffic, which I couldn't have done before, because you can use SafetyNet like to like prevent your app from being modified, and then your app just like runs in its like app sandbox and just like, and you don't like see any traffic. So it's like really like a stacked security mechanism. And if you can like knock out this like one layer, you can like do a lot of bad things. The app integrity checks really like are calculated like on the APK on your disk. So, but Android doesn't actually execute the APK because the APK is like basically a zip file and it contains a bunch of files like DEX files, which is basically like the bytecode from like the virtual machine. And like on all the Android versions, this would be interpreted. Then there was like an optimized version. And since Android 4.4, you could switch it to like their ART runtime, which is basically they compile the bytecode to like native code and just execute that. It's much faster. But that means this like optimized or compiled code is outside of the APK, and the integrity protection is like on the APK. So the obvious task is like, hey, can we tamper with like the compiled code that's actually executed? And there was like 2014, there was like a talk around this where like basically they used this kind of attack to modify like the Android OS core libraries. The funny thing is like I didn't know about the talk. I was like I was messing with like the optimized DEX files and playing around with code injection. Like I have done a lot of work on like DEX dynamic instrumentation, so I knew like the VM pretty well and like how everything worked. And then I was not sure about one thing, and I Googled, and yeah, that since this guy like did like very like the exact same research just for a completely different purpose. I found that's the slide deck which I never heard before. It was pretty interesting, but yeah. So like how does code actually run on Android? So on Android 4 and 5, you have like your APKs are like in data app, and then you have like your your like app name.apk. But the actual data of the app is like in data, and then you have like your package name. And in 4 and 5, your code is actually in a shared code cache directory in like data Dalvik cache. And that code is directory is owned by system, and only like the system user can like actually write to it. So your app cannot, or even your app cannot read it because of the execution model. Your app doesn't need to read it because Zygote, when it forks your app, it will like load that into memory and just like start executing. So you have like apps have no business like reading that code. On Android 6 and later, they changed the layout of the file system a bit. So like all of the apps are like in data app, and then you have like your package name as a directory, and then you have your APK, and your optimized code is like all in one place. But even if it's like your own apps like container directory, certain subdirectories are only readable, are only writable by the system user or install D. And install D is like the service that like actually installs an application which like creates the directories and like starts like the DEX compiler. So you can the mechanism is exactly the same. Your app can still not read like your optimized bytecode. Yeah, because like Zygote loads that into memory for you. So how does like ODEX modification actually work? In a very generic way, you use APK tool like to unpack your binary. You modify the code, then you use APK tool like repack it, use jar signatures like sign it, and then you have a modified APK. It has like the wrong signature. Let's see. It's gonna. Yeah, I'm gonna like do a full demo at the end if I have the time. And then you're like on the device you have to like compile it, basically just convert the DEX code, the bytecode into native code, and just like run DEX to out, and then you have the ODEX of your modified APK. But on your device, say you can just like arbitrarily, like say you have root on your device, you can arbitrarily override the DEX file. The VM will still, or Zygote will still figure out, hey, this ODEX file does not match like the APK file because there's like a very stupid and simple CRC, just like a CRC over the DEX file that the ODEX file is based off, and since you modified the APK, but you only overrode the ODEX, the ODEX file in the APK is not the same you generated your ODEX from, so it will just like recompile. That's basically how the upgrade process works. You just like write a new APK to the file system, and when you start, it's like, yep, we need to, that doesn't match. So what would you obviously like do? You just like patch the CRC to match like the old, the original DEX file, and I made a very simple tool for that to just like automate it. You can just like say, hey, here's like an ODEX file, here's another ODEX file, here's the CRC, replace CRC. And that really, like this attack basically works on all Android versions. Of course, you have to have a rooted device. So you would like overwrite the ODEX file, then stop the application, and you like win. And of course, on like some device, you would just then like maybe remove like the root, so you unroot the device, move maybe just like on the Nexus 7, I can just like now delete like SU and so on, and the application will be modified and it's persistent. Like you can reboot the device, restart, stop the application. As long as you don't touch the APK, that code will like not be touched again. And with this, like you completely bypass the APK integrity check. It's just over. But this is kind of boring. Like, right? If I root the device and I have like system privileges already, I could also just do dynamic code injection. So I thought like, hey, there must be other ways to do it. And like, so the goal is, your basic goal when you want to like attack this is like you want to override this like ODEX file because it contains all the code of the application. So like who can really write it? So if like any processor has like system privileges, and that's actually not true. Actually only install-D and Zygote can write to like your ODEX files or to like system-wide ODEX files. And that means like if you can compromise either of those processes or like get your code running and like inside there as a Linux context, you win. But there's also like interesting OS bugs every now and then. And so there was this bug like last year, Dirtycow, which is basically a race condition in the Linux kernel's handling of memory pages. So basically, the bug allowed you to like overwrite any file on the file system that you can read. So if you can open and read a file, you can also write to it. That was like the essence. It was like, hey, that's like just what we need, right? We can read, because as a shell user, you can actually read the base.odex file. The application itself cannot read it, but if you just get like an ADB shell with like unprivileged user, you can just like overwrite that. And with that, you can basically just do the same attack without rooting the device at all. If your kernel is vulnerable to Dirtycow, you can do this attack. The only like downside is you can so like say you modify your app, you increase the size might increase because you might like put some code in there, but Dirtycow doesn't allow you to like write past like the file boundary, so you basically cannot append. But one easy trick is that if you like know how like ODEX and all of this stuff works, basically DEX to ODE is like an LLVM-based compiler. So you can, and compilers have optimizers, and normally like to get something like fast, you just like do CPU optimization, which often like blows up the binary size. So you can just like compile without optimizations, and then even you added a bunch of code, your output file is smaller, and you can just like easily Dirtycow and overwrite your target. So I'm going to do a short demo. I have only a few minutes left. Basically, I have like a Nexus. No, like it's like some BLU device. It's like those devices are like $50, so it's like really good research devices. This is like way too bright. Yeah. Oh, come on. Anyway, so this is basically the device is like unrooted, secure boot is on, like no modifications whatsoever, and just like this app is running. Let's do a quick demo. So what do we want? So like sa.apk is just like the unmodified APK. So what we're gonna do is just gonna quickly unpack that. So I'm just going to open like one of like the main activity of the app, and the other one is like the code we're going to inject. So this is like if anybody wants any additions to like the greeting we're going to display. Let's see, just like we copy this, and obviously you can like instead of like showing a pop-up, you can just like do like inject like maybe like native like some like a call to like load library or something, and then you can just like inject like your own like code into like the app. But basically you can just like paste this in here, and then we're just gonna build, and building is really just like we're gonna repackage that, and then we just gonna call jar signer with like the default signing key, which is like basically if you installed the Android SDK, you have that to like. And it's Android is the password for the default password for this. So now we have this like the APK. So what we need is like to patch the CRC. So the first thing we're gonna do, first we need to compile the new or a new patched. We have to compile like the patched code, local temp. So we have like our APK, ODEX to ODEX. We have to also do. So now we just like have, this is what we're gonna do. Then we're gonna get like the original like ODE file, pre-compiled version of like the modified app. I just like run the shell script so I don't have to remember the long path name. So this is the original one, so we're just gonna go ADB pull data temp. So now we have the two files. Look, our new one is like a little bit smaller, even we added some code. Like this small tool I built is basically just like shows you some stuff, and so like the base class, that's the CRC. It's the other one, and now we can just like what we do here. It looks like, hey, we want to modify this with this. Then if we run this again, it's like, hey, all CRC. So now we're just gonna push base. Data local temp. It's gonna like quickly stop the application. And now we just do Dirtycow base device mod. Data app. So just override this, and then we can go back, and we can. I have to I'm gonna restart it. It's just don't know if you saw the pop-up. There we go. There's this pop-up, which is now in the app, and we're still 100% passing all of the checks. Yeah, and remember, that doesn't really require routing. So what's the impact? Yeah, it's really limited to Android devices that still have a kernel that's vulnerable to Dirtycow. Probably there's a bunch. Obviously, the attack goes way beyond SafetyNet Attestation. On Android 7 devices, actually the checking against Dirtycow is part of their certification. So Android 7 devices that are certified will never have this vulnerability, which is really good. I told Google about this generic SafetyNet bypass over a year ago, and they were like, yeah, we kind of know about it. And it's that's kind of not cool because it's breaks one core functionality of your thing. Copperhead OS is this hardened Android clone, and they actually mitigate this generically by just recompiling the app at every startup. A little bit slow, but it's a nice mitigation. Some quick observations. Look, so SafetyNet is really improving all the time. So in mid-2016, I saw hey, there's this new basic integrity thing which was not documented. And then earlier this year, I was hey, they have this advice thing which is hey, lock your bootloader or reinstall your OS. So you can see constant improvements. And the basic integrity is now documented, but it wasn't at the time. This advice thing is still not documented. Sometimes SafetyNet has outages. So attestation is based on the CTS data. And CTS data is submitted by manufacturers, including Google themselves, to their own database. So if some data is missing, or the data is false or broken, the attestation will believe, hey, your device has been modified. So Google broke attestation for their Nexus devices themselves by not correctly populating their internal database for a security update to their Nexus 6. So they broke SafetyNet and Android Pay on all of their devices and had to roll back some firmware. So if you're running SafetyNet, you kind of want to have a mechanism where you can hey, we can just disable this for a short time because you don't want to kick out all our customers. And I also saw the same behavior with a Yota phone. It's some small, I think, Russian brand where they had installed a security update or rolled on out, and SafetyNet was not happy with that, and yeah. Google is really playing the cat and mouse game with the routing community, and they detect and lock out new routing methods. So basically, they're just improving. The routing community just makes sure Google is on top of their game and just patching and updating their detections, which is really awesome because you get free, up-to-date security for your app. Also, SafetyNet Attestation is free, so you basically get a good platform service for free, but you also don't have any service level agreement, so you can get rate limited if they get overcapacity, or if they shut it down, they just shut it down. If they have an outage, you can't really complain. So you have to make sure you can deal with that and detect that, and not kick out all of your customers just because Google has an outage. And it's not oh, Google will never have an outage. Service that, an outage doesn't mean the service is down. It just means maybe they're responding very slow, or maybe they don't have information about the device you need to have. One fun thing is attestation is basically also interesting to counter repackaging malware. So a lot of Android malware basically repackage some normal application and just add some bad functionality. So if they actually want to keep the application running, and you have SafetyNet well integrated in your service, you can counter repackaging because the app will just not work. And if they remove SafetyNet and you can detect that, like, hey, this app is not running SafetyNet anymore. You can just like make it completely unusable. So if you don't want like bad people abusing your like popular app for like malware or for malicious purposes, that's like one like easy way to do it. Yeah, that's it. So summary is SafetyNet Attestation is like really the platform security service on Android, and if you're serious about app security, you should really use it. Implementation is like relatively easy. I really hope like this talk, and I'm going to put slides online, is going to help. Bypasses exist, of course. Like now, no security mechanism is like works in all of the cases, but the majority of apps and devices will just like be fine and benefit. It will get better over time, of course, and they're constantly improving it. And that's it. There will be some slides and materials and tools online. I have like this blog where I like monthly like blog about mobile security stuff, not only Android, but like everything that's going on and like interesting stuff. And that's it. I'm a little bit over time. And yeah, if you still will answer questions, otherwise find me in the hallway. And yeah, you can do other fun stuff with Dirtycow too, but no time for that. Yeah, that's it. Thank you very much.